Hi all, welcome to new class. Today's class is about the type number of control systems, then steady state error, etc. So, type number of control system. The type number is specified for loop transfer function. So, loop transfer function is g of s, h of s. So, this is called a loop transfer function, and the type number means the number of poles of the loop transfer function lying at the origin decides the type number of the system. So, the number of poles of the loop transfer function lying at the origin decides the type number of the system. So, in general, if n is the number of poles at the origin, then the type number is n. So, the loop transfer function can be expressed as a ratio of two polynomials in S. That is k into p of s divided by q of s. That is k into s plus z1, s plus z2, etc. divided by s raised to n into s plus p1 into s plus p2, etc. So, here this Z1, Z2, Z3, etc. is called the zeros, zeros of transfer function, and P1, P2, then P3 is called poles, poles of the transfer function. And K is a constant and N is the number of poles at the origin, that is S raised to N means this is the number of poles at S is the number of pole at origin. So S raised to N means this N is the number of poles at origin, and which is called the type number of the control system, and this value of n in the denominator polynomial decides the type number of the system. So if n is equal to 0, then it is called type 0 system, and if n is equal to 1, then the system is type 1 system. If n equal to 2, it is called type 2 system, and so on. So this is about the type number of control system. Next is steady state error. The steady state error is the value of the error signal E of t. So E of t is the error signal, and steady state error is the value of E of t when t tends to infinity. That is, it is denoted by ESS, and that is equal to limit t tends to infinity E of t. So, the steady state error is the value of error signal when t tends to infinity, and the steady state error is a measure of system accuracy, and these errors arise from the nature of input, then type of the system, and from non-linearity of the system components. The steady state performance of a stable control system is generally judged by its steady state error to step, then ramp, and parabolic inputs. So consider a closed loop system. Here R of s is the input signal, E of s is the error signal, then C of s is the output signal or response, then this is the feedback signal and its value is C of s, H of s. Then here this is the error signal, and we can write error signal E of s is equal to this R of s minus C of S into H of S. But we can write this C of S is equal to E of S into G of S. That is C of S equal to E of S into G of S. Now substitute the value of C of S in this equation. That is substitute equation 2 in equation 1. We get E of S equal to R of S minus C of S is E of S G of S into this H of S. Now we can combine this E of S together. So E of S into 1 plus G of S H of S is equal to R of S, or we can write E of S equal to R of S divided by 1 plus G of S H of S. So error signal is this one, and this is in S domain. So the error signal in time domain E of t is equal to L inverse of E of S, and that is L inverse of R of S divided by 1 plus G of S H of S. And to get the steady state error ESS. ESS is the steady state error. So steady state error is defined as the value of E of t when t tends to infinity. So ESS is equal to limit t tends to infinity E of t. And we have the final value theorem. Final value theorem. If f of s is equal to Laplace transform of f of t, then we have limit t tends to infinity f of t is equal to limit s tends to 0 s into f of s. So this is the final value theorem. That is limit t tends to infinity f of t is equal to limit s tends to 0 s into f of s. So using this final value theorem, we can say use this. So we can write the steady state error ESS is equal to limit, this is limit t tends to infinity E of t. So that is equal to limit s tends to 0 s into E of s, and E of s is R of s divided by 1 plus G of s H of s. So we can write limit s tends to 0 s into R of s divided by 1 plus G of s H of s. So this is steady state error using final value theorem. So steady state error is ESS equal to limit t tends to infinity E of t, and that is equal to limit s tends to 0 s into R of s divided by 1 plus G of s H of s. Next is static error constant. When a control system is excited with a standard input signal, the steady state error may be 0, constant. So ESS may be 0, then constant or infinity. And the value of steady state error depends on the type number and the input signal. So for type 0, type 0 system will have a constant steady state error when input is step, and for type 1 system a constant steady state error will occur when the input is unit ramp signal or velocity signal. And for type 2 system, it will have a constant steady state error when the input is parabolic signal or acceleration signal. And for the three cases, the steady state error is associated with some constants. That is, the main constants that are related to the steady state error are positional error constant, and which is defined as Kp is equal to limit s tends to 0 g of s h of s. Second one is velocity error constant. Velocity error constant is Kv is equal to limit s tends to 0 s into g of s h of s. The third one is acceleration error constant. Ka is equal to limit s tends to 0 s square into g of s h of s. And here this Kp, Kv and Ka are called the static error constants. So the steady state error is associated with one of the constants which are called the static error constants, and that are positional error constant Kp, velocity error constant Kv and acceleration error constant Ka. So let us find the steady state error when different input are applied. So first one is steady state error when the input is unit step signal. So the steady state error ESS is limit s tends to 0 s into r of s divided by 1 plus g of s h of s. So here when the input signal is unit step, so r of s is equal to 1 by s. So we can write ESS equal to limit s tends to 0 s into r of s is 1 by s divided by 1 plus g of s h of s, and we get limit s tends to 0 1 divided by 1 plus g of s h of s. And here we can apply this limit to these terms, and we get 1 divided by 1 plus, because here no s terms, so only s term is this one. So here we can write 1 divided by 1 plus limit s tends to 0 g of s h of s. And this one is, that is limit s tends to 0 g of s h of s is we have already defined as the positional error constant Kp. So we can write 1 divided by 1 plus Kp. So Kp is the positional error constant. Then let us check for different type number of the system this value, that is the value of this positional error constant for different type systems. That is, for type 0 system, Kp is equal to limit s tends to 0 g of s h of s, and that is equal to limit s tends to 0 g of s h of s is k into s plus z1 into s plus z2 into etc. divided by s plus p1 into s plus p2 into etc. So here while applying limit s tends to 0, so here we will get a constant term, because while applying s equal to 0, here we get z1, here z2 into etc. Also here while applying s tends to 0, we get p1 into p2 etc. So this value will be a constant. So Kp is equal to a constant. That means the steady state error ESS is equal to 1 by 1 plus Kp. So when Kp is a constant, we get the steady state error a constant for type 0 system when the input is unit step signal. And for type 1 system, Kp is equal to limit s tends to 0, g of s, h of s. And here for type 1 system, we will have k into s plus z1 into s plus z2 into etc. divided by, so type 1 system means here the value of n is 1, so there will be s in the denominator, then s into s plus p1 into s plus p2 into etc. So while applying s tends to 0, here we get z1 z2 etc. divided by here 0 into p1 p2 etc. So 1 divided by 0, that is we get 1 divided by 0, that means it is infinity. So Kp is infinity and we get ESS equal to 1 divided by 1 plus Kp, and that is 1 divided by 1 plus infinity, that is 1 divided by infinity. 1 by infinity means it is 0. So for type 1 system, the steady state error is 0 when the unit input is unit step signal. And also for the type number 2, it will be s square. So the Kp will be also equal to infinity in that case, and ESS will be 0. So if systems with type number 1 and above, for unit step input, the value of Kp will be equal to infinity, and so the steady state error will be equal to 0. Next is steady state error when the input is unit ramp signal. So steady state error ESS is limit s tends to 0, s into r of s divided by 1 plus g of s, h of s. So when the input is unit ramp signal, this r of s is equal to 1 divided by s square. So we have ESS equal to limit s tends to 0, s into 1 divided by s square divided by 1 plus g of s, h of s, and that is equal to limit s tends to 0, 1 divided by, here we get s here, so we can write s plus s into g of s, h of s, and applying this s tends to 0 for these values, we get, while applying limit s tends to 0, here we get 1, then here we get 0, that is s plus term is there. So here limit s tends to 0 means this value is 0, then here limit s tends to 0, s into g of s, h of s, and here limit s tends to 0, s into g of s, h of s is, we have already defined it as the velocity error constant kv. So this is 1 divided by kv. So ESS is 1 divided by kv for unit ramp signal, where kv is limit s tends to 0, s into g of s, h of s. Now we have to define these values for different type systems. So for type 0 system, we have kv is equal to limit s tends to 0, s into g of s, h of s, and we can write limit s tends to 0, s is there, so s into k into s plus z1 into s plus z2 into etc. divided by s plus p1 into s plus p2 into etc. So while applying this limit, we get here z1 z2 etc. here p1 p2 etc. but here there is s, so while applying s tends to 0, here we get this value as 0. So kV is equal to 0 for type 0 system when the signal input is unit ramp signal. And also the steady state error ESS is 1 divided by kV, and that is 1 by 0, that is infinity. Now for type 1 system, we have kV is equal to limit s tends to 0 s into g of s h of s, and that is equal to limit s tends to 0 s into k into s plus z1 s plus z2 into etc. divided by, for type 1 here s into s plus p1 into s plus p2 into etc. So while applying this limit here this s we can cancel, so here while applying this limit we get z1 into z2 etc. divided by p1 into p2 etc. So we get a constant value. So kV is a constant for type 1 system in the case of unit ramp signal, and we get ESS, that is the steady state error, equal to 1 by kV, and that is equal to a constant. Now in the case of type 2 system, we have kV is equal to limit s tends to 0 s into g of s h of s, and that is equal to limit s tends to 0 s into k into s plus z1 into s plus z2 into etc. divided by, this is type 2 system, so we have s square into s plus p1 into s plus p2 into etc. So while applying, and here we can cancel one s here, so while applying this limit we get 1 divided by 0, that is equal to infinity. So 1 by 0 means infinity, so kV is infinity, and we get the error signal ESS equal to 1 by kV equal to 1 by infinity equal to 0. So with if the systems will have type 2 system or above, for unit ramp input the value of kV will be equal to infinity, and also the steady state error will be equal to 0 for type 2 and above systems in the case of unit ramp signal. Next is steady state error when the input is unit parabolic signal. So we have ESS equal to limit s tends to 0 s into r of s divided by 1 plus g of s h of s, and for unit parabolic signal this r of s will be equal to 1 by s cube. So ESS will be equal to limit s tends to 0 s into 1 by s cube divided by 1 plus g of s h of s, and that is equal to, here we get 1 divided by s square, that is limit s tends to 0 1 divided by s square plus s square into g of s h of s, and while applying this limit here we get 1 divided by, here while applying limit it is 0 plus limit s tends to 0 s square into g of s h of s, but this is the acceleration error constant, so we can write 1 divided by ka, where ka is equal to limit s tends to 0 s square g of s h of s, and it is the acceleration error constant, so ESS is equal to 1 divided by ka. Now for type 0 system, Ka is limit s tends to 0 s square g of s h of s, and we can write limit s tends to 0 s square into k into s plus z1 into s plus z2 into etc. divided by s plus p1 into s plus p2 into etc. So while applying this limit we get it is 0. That is Ka is equal to 0. That means ESS, that is the steady state error, is equal to 1 divided by Ka, and that is equal to 1 by 0 equal to infinity. Now for type 1 system we have Ka is equal to limit s tends to 0 s square g of s h of s, and that is equal to limit s tends to 0 s square into k into s plus z1 into s plus z2 into etc. divided by, for type 1 system there will be s into s plus p1 into s plus p2 into etc. So while applying this limit, here we can cancel one s, so we get s into, so while applying this limit we get 0. So Ka is equal to 0 and we get ESS, that is the steady state error, equal to 1 divided by Ka equal to 1 by 0 equal to infinity. Now for the type 2 system we have Ka is equal to limit s tends to 0 s square g of s h of s, and that is equal to limit s tends to 0 s square into k into s plus z1 into s plus z2 into etc. divided by, for type 2 system here there will be s square into s plus p1 into s plus p2 into etc. So here this s square get cancelled, and while applying this s tends to 0 limit we get a constant value. So Ka will be equal to a constant, and we get the steady state error ES is equal to 1 divided by Ka, and that is equal to a constant value. Now for the type 3 system we have Ka is equal to limit s tends to 0 s square g of s h of s, and that is equal to limit s tends to 0 s square into k into s plus z1 into s plus z2 into etc. divided by, for type 3 system there will be s cube into s plus p1 into s plus p2 into etc. So here this s square get cancelled, but there will be 1 divided by s here. So while applying s tends to 0 limit we get 1 by 0, that means 1 by 0 is infinity. So Ka is equal to infinity, and we have steady state error Es is equal to 1 by Ka, and that is equal to 1 by infinity equal to 0. So in systems with type 3 and above, for unit parabolic input the value of Ka will be equal to infinity, and hence the steady state error will be equal to 0. And this is the table which describe the steady state error for various types of inputs. So this is the type number, and this is the steady state error when different input signals are applied. So for type number 0, and when the input is unit step, the steady state error is 1 divided by 1 plus Kp, and when unit ramp signal is applied ESS is infinity, and for unit parabolic signal infinity. Then for type 1 system, here for unit step ESS is 0, for unit ramp 1 by kV, for unit parabolic it is infinity, and type 2 system for unit step and unit ramp it is 0, and for unit parabolic it is 1 by Ka, and type 3 system all are 0. So that means for type 0 system a constant steady state error is obtained when unit step signal is applied, and type 1 system constant steady state error is obtained when unit ramp signal is applied, and type 2 system a constant steady state error is obtained when unit parabolic signal is applied. So this is ESS. So that is about the type number, steady state error, and the static error constants. So thank you for watching the class. If you like the classes, Please like, share and subscribe my channel.